Excellent. Well, welcome everyone to part two of the Google Cirq workshop. Tanu's had a really great presentation before, and now Balan's gonna take it away for the second half.
All right. Thank you, Tanush, for the thorough introduction. So let's jump in. We have like 50 minutes or so, and maybe we might run over the hour a little bit. So thank you for your patience on that. Cool. Let's try to squeeze in as much as we can. So let's talk about gates. So as we discussed, gates are the main language of quantum computing today. In the end, all we do with a typical quantum algorithm is decompose an n-qubit unitary to gates. So what do I mean by that? I mean that when we ignore the noise, the true transformation of a quantum state is captured by a unitary matrix, and gates just make it more readable and easier to handle by human beings. So Cirq has something called protocols, and the unitary method, you've already seen what it does. So if I print this out, you can see the unitary matrix of the CNOT gate. We can do the same thing with the circuit up here. So if I create these operations and then insert it to the circuit, I'm going to see these this nice ASCII diagram.
Balin, sorry to interrupt. They're asking if you can increase the font size a bit.
Yes, I can totally do that. Is it better?
Let's see. Maybe a little more. That looks good on my screen. Let's see. They said thank you. All right, we're good.
Okay, sounds good. Thank you. Thank you for the feedback. So this is how the circuit looks in ASCII diagram. But if I print out the actual unitary of it, we'll see that it's not that readable. So we have this 8 by 8, right? Because we have 3 qubits, so 2 to the third power of 3 is 8. So it's an 8 by 8 matrix. So this is what's really happening in a quantum algorithm. But instead, we use gates and the circuit representation to make it more manageable. So I wouldn't say that the gate and circuit language is really intuitive, but it's definitely better than the big matrices. So what we have here is the poly X, Y, and Z gates. We have the controlled Z, the controlled NOT gates, and then 3 qubit gates as well. So these are typically the 1, 2, and 3 qubit gates that we use in devices or in quantum computing literature. In Cirq, we use the convention to put everything interesting in the Cirq namespace. So when you enter Cirq dot and you press Control Space, for example, you will see all the interesting things. So you enter a C, then you will have all the controlled stuff there. I just wanted to point that out. So one more thing I wanted to just show here is that Cirq allows for exponentiation of gates. So this here is a square root of the X gate. So that's a valid thing to do. And that's something we can do with the Z gate as well, for example. So the unitary of the Z gate is this. And if I exponentiate to 1/2, so the square root of the Z gate, I'm going to get the S gate. So you see that these two are the same unitaries. And if I take the square root of that, then we're going to get the T gate. All right. Other interesting single qubit gates are the rotation gates, Rx, Ry, and Rz, which are rotation gates alongside the block sphere axis. So let me just show that for a second in Qwerk. So Qwerk is a tool that Craig Gidney wrote, who's one of the original authors of Cirq. And we will have block sphere representations and illustrations in Cirq as well in the coming months. But for now, this will serve us really well. So here in Qwerk, which you can reach on olgaser.com/Qwerk, we see the block sphere representation of each of the qubits. And then I have a changing Rx, Ry, and Rz rotation that shows the actual interaction, what's happening with the qubit state. So the qubit vector is rotating around the x-axis, it's rotating around the y-axis, and here I have to put it first into the plus state, the qubit, and then I can rotate it around the z state, and then we can see that it's processing around the z axis. If I don't have this here, then it's still processing around the z-axis. It's just invisible because it's just rotating in place. So this is a bit more valuable to see. Another thing we can see here is the chance of being on measured, and which means that if we would measure this qubit and the computational basis, we would either measure 1 or 0, right? And then this shows the chance of measuring 1. So we see that it oscillates as time goes by. So as the angle of the rotation changes, the probability of measuring 1 oscillates. So this is what we're going to do now in Cirq, and see how we can simulate this. So we prepare a qubit, and using that qubit, on that qubit, we're going to create tiny little Rx rotations that will rotate at each step, 200 steps, basically, for 1/50th of a half turn. So that's 200 by 1/50th, that's 4 pi. So that's 2 full rotations around the x-axis. And then we're going to use the simulate moment steps method of the simulator, which allows us to go through the circuit one by one, moment by moment, just like you would do on pen and paper, trying to figure out at the state of the system at each moment. So it provides an iterator of steps, and in each step, we have access to the state vector. And then in the state vector, we have the probability amplitudes, and then we can convert those to actual probabilities. So we'll know the exact probabilities of measuring 1 in our simulation. So if we plot this, and we'll see this nice cosine curve. And so access to the state vector is impossible in real devices. So what we usually do is sample. This is what Doug mentioned as well in the quantum chess presentation, that we have this duality of simulation and sampling. So in simulation, you have access to the state vector. In sampling, you only have access to measurements. And so this is what we, there's another nice utility function here that allows sampling without even measuring. So this is still from the simulate moment steps iteration. You get a step at each moment, and then you can sample from that step for a given qubit, and then you can set how many times you're going to repeat that sampling. So this is important because we're going to get the estimate of the real probability of measuring 1 or 0. Here, in case we're measuring 0, because we're getting the first element of the probability amplitudes. And we're going to take the average of these measurements, these samples, and that's going to be our estimate for the real probability. So if I start with 10 repetitions, for example, and we'll see that this is a kind of a wave. Oh, my mouse is not scrolling for some reason. So this is a nice kind of wave, but it's not perfect. So if I increase the number of repetitions, then my estimated probabilities are going to be much more precise and follow much more closely to the theoretical ideal probabilities. All right. So sometimes you might want to use some gates that are not built in Cirq. In this case, it is possible to define your own gates. in order to do this, you'll have to create a class and implement some simple magic methods. So let's talk a little bit about protocols here. Protocols are basically a contract or interface. If your class implements some magic methods, you will unlock some special operations or syntactical sugar. For example, the square brackets in lists and maps in Python are there because those classes implement the container protocol. So you implement underscore, underscore contains, underscore, underscore. We call this double underscore or dunder methods. Or the set item dunder method, or the get item and the get item dunder methods, and then you will be able to use the square bracket on them. So similarly, in Cirq we have protocols which are on our website listed in the quantumai.google/Cirq/protocols page, and there's more explanation here as well. So one of them is the Unitary Protocol that you will have to implement in order to implement your own gate. So let's pick a fun gate. A gate has to be unitary. Recall that a unitary means that the product of the matrix and its adjoint are conjugate, or conjugate transpose is the identity. So we use this Pythagorean triplet to define a unitary matrix, which, by the way, we don't have to do a complicated product calculation to check whether that's unitary or not. We can use Cirq that is unitary and then pass in this array that we're gonna return from our underscore unitary underscore method, which is our magic method. So I'm just gonna prove this to you. If I print this out, it's true, it's unitary. So if you didn't believe me that this is unitary, you can believe Cirq. Great, so we have now this class called rational gate that inherits from single qubit gate class, which could be the gate class, but then I would have to define the number of qubits to be 1. This is a convenient parent class to just instantiate single qubit gates. We also have 2 qubit gates, we have 3 qubit gates, and we have just the gate as well. So I'm just going to leave this here as a single qubit gate. Another thing here is to mention is that we provide the string representation of the gate so that when we display it in circuits, it will print nicely in our ASCII diagrams. Beautiful. And then we can see the unitary of our rational gate works. Another cool thing is that as soon as you have a unitary, you can use this gate directly in simulators. So we'll see that the simulator results in a state vector that what was expected. Great. So exercise time. Let's create a custom gate that will be a 2-qubit controlled gate that will that has this following unitary, and this will do basically CRX. So if I would do this here, I can just show that to you very quickly. Move these. This guy down here. I see that it's rotating. And if I create a controlled version of the RX gate, then it doesn't do any kind of rotation if the control qubit is 0. But if the control qubit is 1, then it starts rotating. And by the way, this is kind of fun that you can see the superposition of rotating and not rotating if you put a Hadamard gate there. Anyway, so let's go back to the exercise and attempt your solution here. And I'm going to stop here for questions and give you 2 minutes for the exercise, and then we'll continue from there. Any questions on Twitch?
There are no questions so far. We have one person who has said that they're trying. I'm sure there are more.
Oh, thank you very much. Yeah, please do chat if you're trying or if you're done. It gives us a good feedback around whether we should go forward or not. Can we construct nonlinear transformations? See that question. So what do you exactly mean by that? So quantum mechanics in itself is linear. So we are limited by that math, and that's why everything is linear. So if you can elaborate on that question a little bit more. Yes, the Hilbert says evolution is unitary. So that's one of the axioms of quantum mechanics, which makes our lives simpler. I think that there were some results around that if there would be nonlinear quantum mechanics that would create some impossibilities. Okay, this is my count for 2 minutes. Great. So let's see what the solution is. So the solution is to actually just write down this matrix as it is. So 0, 1, and then I can do a little bit of trick here. I will do C equals MP plus self dot theta. S will be MP sinus self dot theta. And then, so CCS nicely, and then minus 1J S, minus 1J, and then we can print out the unitary. The comma. Type. There it is. So that's our solution, and theoretically this should be exactly the same as here. Theta over 2, I forgot to do that. Yes. So we need half angles. Great. How's theta initialized? Should we pass it as an argument? So yes. So the way this works is that if you pass in theta into the constructor, then you get a gate that rotates at that angle. And then you can use that after that in a circuit. You can pass it in as you can pass a qubit into it with another set of parentheses. So that's going to be your operation afterwards. I hope this answers the question. Oh yeah, another difference between my solution and the prepared solution is that if I use my version in a circuit diagram, it will have this default string representation that is a little bit ugly. So with 1 qubit gates, we saw that just overriding underscore str underscore can provide a nice symbol. For 2 qubit gates or multi-qubit gates, you will need to implement the circuit diagram info protocol by implementing the magic method circuit diagram info, and then you return back the per qubit, per each qubit, the symbol on the wire that you want to see. So if I do this instead, then my circuit diagram becomes much nicer. Great. Let's jump into gate decompositions. So quantum algorithms can be run on different simulators, hardware implementations, or quantum error correction codes. these can limit what kind of operations, what kind of gates one can execute. So this is what a gate set is. Gate sets were the original motivation for introducing decompositions. It also allows for the second way of defining a gate by its decomposition. For example, if you want to create a gate that consists of Hadamard gate and the X gate, we can create it by implementing the underscore decompose underscore magic function. Yes, this is another protocol that supports decompose protocol. And as soon as gate has decomposition defined, it can be decomposed, which is useful in simulation and compilation. So we can compile this gate. Let's create this gate in the circuit. So, oh, I forgot to run the first cell. So we have our gate created. And we see that in a circuit, it will just display as HX. It's a single gate. It's not two gates, it's just a single gate. And now we can use compilation methods called decompose that will compile my circuit into an equivalent circuit, but into smaller gates. All right, so this is interesting. We can understand that we have, when I decompose H and X, we have X at the end, but what is this? So this, square root of Y and X, is how the Hadamard gate decomposes in Cirq by default. So this might be something that we like, might be something we don't. So Cirq gives you a lot of control over how decomposition can happen. For example, you can just say you don't want to decompose to the bottom layer recursively. You just want to do one layer of decomposition first. If in case you do that, then you get the single decomposition of H and X. Another tool that you can use configure your decomposition with is the intercepting decomposer that can pre-process your circuit before the default decomposition logic kicks in. And so it scans, so Cirq will scan your circuit, and for each operation, you have the chance to do your own decomposition. So in this case, we'll say that for the HX gate, when I recognize that the operation is the HX gate, return Z and H, which is incorrect, but it's it shows that we can circumvent the decomposer. So now we see that we have Z and H, which is again the square root of Y and X. So that's the intercepting decomposer. Another, and then the final piece of decomposition logic that you can do here is the keep argument. So when you pass that in, you can say that, okay, if anytime throughout the decomposition of operations to smaller operations or different operations, you encounter certain operations, keep those, don't decompose those. So you can protect gates in your gate set from being decomposed further than you need them to be. So this keep function, this predicate, will return true. So we'll say, yes, keep it, if my operation is a Hadamard or an X operation. And so if we run this, again, the decomposition will show for this operation, it will return a list of operations, which is an H and an X operation on the A qubit. Great. Next topic. So these are a lot of little topics that might or might not be interesting for the Google challenge, which, by the way, I'm taking full responsibility of not being completely opened just yet. We will announce it on Saturday if we can get through all the approvals. There's one or two approvals are still missing. So it's a little bit of a hackathon for ourselves as well. So if there will be a Google challenge, then these information that I'm sharing now might or might not be useful. Great. So parameterized circuits. In addition to circuits with fixed values, Cirq also supports parameterized gates. So why is this useful? So real hardware today typically sits in a data center. Cirq is running on your laptop. You create a circuit, send it over some sort of API, sample from it. Remember the difference between sampling, where you only have access to measurements, versus simulation, where you have access to the wave function or the state vector. So you sample from these circuits and get back the measurements through the wire. There are a lot of experiments. For example, the Rabi oscillation experiment that we did there with the probability of 0 being measured or 1 being measured. If you remember, we had the 200 tiny RX rotations in the simulator. It would be very expensive to send 200 circuits and get their measurements back and forth between the data center and my laptop. Instead, parameterized circuits were introduced to help with the execution of these type of experiments. Cirq supports the creation of parameterized circuits that are like regular circuits, but certain things like the exponent or the rotation angle of a gate can be symbolic variables or parameters. We rely on SymPy, which is a Python library for symbolic mathematics. So in this cell, we have the 2 qubits, and we have a symbol S stored in this val variable that we'll use to be the exponent of these 2 X rotations on my two qubits. So this looks like this. This circuit doesn't have a unitary because we don't know what it is, because we don't know the parameters. We have to resolve these parameters somehow before we can use this in simulation or use this in sampling. So what we do is we have to pass in a parameter resolver. Now, a param resolver is basically just a dictionary that says that for a given symbol, resolve it to a given numerical value. So here we are iterating with the value from 0 to 1 in 4 steps. So we're going to see how the final state vector, this is still just simulation, will look like. So we'll see that for s equals 0, that's the identity. And by the way, I like the state vector to be presented with the Dirac notation that is a little bit more readable. So we see that we are in the 0, 0 state. And then when we get to 1, so s equals 1 will be X gate on both of these guys. So we'll have 1, 1. And then in between, we have some kind of superposition as we rotate the angles. So what we just did, we ran 5 simulations with different parameters for each circuit. So this is still not the efficient thing that I was talking about for data centers. That's going to be the next thing here. So here we well, still a simulator. I'm not going to demonstrate on real device today, but the concept is the same. We use the run sweep method that allows for taking a list of resolvers for a single parameterized circuit, send that down the wire, and then sample from each of the resolvers that translates to a real circuit, sample 10 times. If you remember the repetitions, the more you increase that, the better estimate you have for the real probabilities, the true probabilities. So we send it in one go and then get back in one go all the results. So let's see one more important thing that I have to mention here is that you have to have measurements, right? So we append to our circuit 2 measurements, one on the A qubit and the other one on the B qubit. And I'm going to print out this circuit just for prosperity. So you see that we have the parameterized circuit in X on the power of S, and then we have the 2 measurements at the end. And what we get back is a list of results, 1 for each parameter resolver. So we have 5 results in one go And then we have the list of bits that we measured. So we have 10 bits measured for each qubit. And we see that the number of ones are increasing as we go from 0 to half. We didn't go up to the full X. If we would go down to the full 1 rotation, then all of the bits would be 1 here. So a very similar method is to run sweep is the sample method, which is exactly the same, but this returns a pandas data frame, which enables you to slice and dice the results more efficiently. So if I show, like, for example, it gives you this nice description of your matrix, but if I show you the actual matrix, you see that the data frame, each column, we get 1 column for the symbol, 1 column for each of the measurement keys, and then for each repetition, we get a row. So if I decrease this to 2, for example, I'm going to get much less rows. So 2 rows for each combination of symbol values, parameter resolvers, and measurement keys. So above here, we created a list of resolvers manually, like this, which is cool. We can do that. But Cirq provides some powerful methods to create list of resolvers, which we call sweeps or sweepables. These sweepables, for example, the lin space or linear space, allow you to just define this as like range. NumPy has lin space, so this is very similar to that. And then we can also do something called points, which I would say that for, let's say we have another parameter called y, and I'm going to list like 1, 2, 3 as parameter values, which seems a little bit boring or similar to just manually creating a list. But what's cool is you can do in Cirq something called, for example, the product, which will create the product of these 2 sweepables. And now suddenly we have these 2 parameters that we can then iterate through, and you have the Cartesian product of the 2 sweepables. Great. So we have the second exercise and last exercise for today. And then after that, I'm going to run through the remaining sections as much depending on the time I have. So let's rotate a qubit. So let's do the equivalent of the Rabi flop experiment. So we're gonna, you're gonna have to put your code in the placeholders. So here, when we prepare the circuit that will have a measurement on this qubit, we have a theta symbol that you will use to create the parameterized rotation of an X gate. And then we're going to sample from the results, and then you can test the result with the following plot. And then we'll see something interesting. If you got that right, you will have to fill out the param resolver as well. So what we want is this X gate to move from 0, so exponent 0 to exponent 1 in 100 steps, and each step need to be measured 100 times. All right, so I'm going to stop here for 2 minutes and then see if there are any questions that I can answer in the meantime.
I don't think there are any new questions. Someone had an error running code in the notebook, but I think Tanu solved that already. So we should be good, or we can wait for a bit more.
Well, thank you. Let me know, guys, if you if anybody's working on it, needs more time, or you're done. We have 6 minutes until the hour. Skip noise. We're going to talk a little bit about devices. And compiling and optimizing.
Somebody just asked, how is sampling simulated?
So sampling is simulated using a pseudo random number generator using NumPy's random state. So it's just that. Okay. I understand that it might be actually late in the day as well as it's lunchtime in Pacific time. And sorry, I have some noise in the background. There's construction next to me. This is the joy of working from home. So okay, so let's jump into it. Oh, somebody was working on it. That's great. I'm gonna just go ahead and then solve it. So what we wanted to do is have an x pow gate. So we're gonna raise x to the power of theta. So this creates a gate, and then we're gonna apply this on the Q qubit. This is my circuit, and then for param resolvers, I'm gonna use linspace for theta. Start from 0 and stop at 1, and length is going to be 100. And then this should give me with sample a nice plot of the probabilities as I go from 0 to 1 in theta. I see the probabilities of measuring 0 decreasing and probability of 1 increasing to 100%. Great. So let's see how much I can fit into like 10 minutes maybe. Devices. Let's talk about devices. Up until now, we talked about ideal quantum algorithms. We could run any kind of gates, even the fun Pythagorean triplet gate. You can run 2-qubit gates between any qubits. However, as we mentioned it today multiple times, real devices are limited. The concept of a device in Cirq is meant to capture exactly these limitations. A device can express what gates are supported, which qubits you can run which gates on, and other things. For example, the Google Bristlecone chip, which is our 72-qubit chip, is okay. Now it's just jumped away. Sorry for that. Is here. If I print it out, it allows 2-qubit gates only between adjacent qubits. So you won't be able to do a CNOT or a CZ between these 2 qubits. Also, for example, you won't be able to do CZs in the same moment, so at the same time, between these 2 qubits and these 2 qubits, because they are next to each other. So the 5-6 and 6-6 are adjacent, and that would there's some kind of physical interaction between the 2 qubits that are not allowed. So these kind of constraints that we can capture in the device class. So Cirq.Bristlecone also tells you like the duration of operations. I'm not sure how precise this is, and we might get rid of it. So don't take this with a grain of salt. This is still in development. We are still working on getting realistic noise models around devices. So it's still a work in progress, this area. One feature though that we can check here, and what I was talking about is these adjacent qubits and CZ operations. And that's something that if I pass in a circuit that does this operation, so 2 CZs on these 2 qubits, then bristlecone will, when I say validate circuit will throw an error that, hey, you have adjacent X11 operations. I'll talk about what X11 is later. And yeah, one even cooler way to access this kind of feature is that if you pass in the device into the circuit itself, so you say that from the first moment of construction, the circuit has the device assigned, then as you append new operations, it can use this knowledge whether something can go into the same moment or not online. So I pass in a list of operations and it will automatically push them into separate moments. So you can see the difference between Cirq.unconstrained device, which is the default one. That's the ideal situation. It allows you to do this, and with the default insertion strategy, which is the earliest, and that Tanush talked about. If I go back to cirq.google.bristlecone, even though the insertion strategy is the same, Cirq will recognize that this device won't allow these two things to run in the same moment, so it will push them further out. I recommend the exercise as a homework, and we're not going to go into this, but you can create a device with your own constraints at home. All right, optimization. So optimization is another angle that is very important for creating quantum circuits. The philosophy of Cirq is that we'll have a few, not that many compilations, basically one or a few passes for a circuit, because there are just so few gates that you can do on a NISQ device. So for this, we created the point optimizer class that you can use to create relatively short code, low amount of code to create interesting transformations on your circuit. So for example, we know that if you have X and Z, that is exactly the same as, or almost the same up to global phase as a Y gate. So what we can do with this circuit optimizer is, if you pass in a circuit that has X and Z next to each other, it will eagerly remove X and Z and instead replace them with a Y gate. So you can do this kind of transformation and tricks here. So and you have to implement this interface and the optimization at abstract method. So you will get the circuit, which you can use to look ahead. You can get the index of the moment and the operation that you're currently looking at. So it's like the visitor pattern, if that says anything to you in object-oriented programming. You visit each of the nodes in your data structure, and then you can mutate the data structure or have some kind of side effect. So that's what's happening here. If it's X, then we'll check what the next operation is. If the next operation is a Z gate, then we're going to return a point optimization summary, which says that, hey, clear the span from this index up until the next operation index, so that these two, this could be just two actually, and then clear qubits that we're using this operation. So basically, this says that clear these two operations, and then insert the new operation, the list of new operations, which is just the Y, and then the optimized circuit method will just use this and create the new circuit. Again, there's an exercise which is actually hard. I would recommend to fight with this a little bit if you have time, because it's enlightening. But we won't have time for it today. Okay, the last topic that I wanted to just touch on in the last 5 minutes is Google's X-Mon gates. So I mentioned that one of the limitations of devices and error correction codes and simulators sometimes is that they have a specific set of gates that they can execute. So in Cirq, we represent this with a gate set. So under the Google devices, so we have Cirq.Google gate sets, and you have the X-Mon gate set. You also have the Sycamore gate set that tells you the Sycamore chip, which is the 54 qubit chip that we use for the quantum supremacy or beyond classical experiment. And we can use this gate set to validate whether an operation is part of it or not. So a gate set is a family of gates. These could be parameterized gates, so they can enable multiple gates to be part of this or described by this. So we have here a rotation around in the X-Mon gate set, rotations around the poly Z axis, rotations around any axis in the poly XY plane. So this gives you the axis on the XY plane. You can see this is a one-dimensional, two-dimensional rotation in the XY plane. And then rotated around that is defined by T. And then the 2-qubit gate, so these are 1-qubit gates. And then the 2-qubit gate is the X11 gate. That's what I was talking about in the previous cell. Is basically, you can think about it as a CZ gate, but applied for different lengths of time. So so CZ gate is just a special case of this X11 gate, where this becomes -1, the control Z gate. Okay, so is supported operations. We can see that X is part of the supported operations here. So that falls under in this family of gates. However, C0 is not supported. C0, if you remember, is a very different unitary. It has 1, 1 here and 0 and 0 on the diagonal on the bottom right block. If I say CZ, that will be true. However, even if you have a gate that is not supported, you can convert it to supported gates. So we provide convert to X-Mon gates. There's also convert to Sycamore gates, which works similarly. And if you call convert on your operation or circuit, then you will get these operations that are part of the gate set. It is much longer, but this is the reality of quantum computing. If you want to express a circuit that in gates that are not supported, you might have to deal with larger circuit depth. However, we can do better than this. We can actually optimize this and squash this together into single qubit gates that are still supported. And this is something that you don't have to do and figure out yourself. We provide the optimized for X-Mon method. There's also optimized for Sycamore. And that will squash these together into this phased XZ gate that is basically this gate just expressed with the Cirq type hierarchy. So that's kind of what I wanted to mention. Yes, you can serialize these operations. So when you send these across the wire, these get serialized into protocol buffers, and this is how it looks like. And then just at the bottom of the introduction here, you can see how like the Rabi oscillation experiment that we did is actually packaged up as a separate experiment that you can run in case of Google QCS or other hardware providers. The sampler can be a real like API. And then, yeah, there's some testing that you can do, testing utilities. And then, as I mentioned in the chat, you can export circuits to OpenQASM, to PyQuil, and even to Quark as well. So, so you can see that this was the circuit that I had there. And that is now the Quark version. All right, so I'm going to stop here for questions, and thank you very much for staying with us this long.
Excellent. So we do have a few questions. I think we'll start with the earliest one. So someone asked, why doesn't Google pursue all-to-all connectivity in its hardware?
That's a good question. A caveat here, a disclaimer, I'm a software engineer and my background is not in quantum computing. I will talk about it a little bit more in the Quantum Journeys panel on Friday. But I know some things. So in this case, my understanding is that the Google quantum team grew from the UCSB, the University of California, Santa Barbara team under John Martinez. They were focused and specialized in superconducting qubits. So superconducting qubits are basically electrical circuits. You use Josephson junctions and you have a chip that is planar, and it is very hard to think in 3-dimension there. So the 2D planar layout kind of forces this kind of grid setup. There are different kind of 2D topologies that you can experiment with, but for certain reasons, Google went with the grid approach. I think one of the reasons is also the surface code that is what we're trying to use for implementing a logical qubit, which also aligns really well with this grid structure. In other architectures like ion traps, you can use all-to-all connectivity that buys you some power, but then there's always trade-offs. So that this answers the question.
Excellent. And someone else asked, approximately what range of circuit depths can we currently implement?
That's a good question, and I won't be able to answer from the top of my head around that. Yeah, but I think it's in the 100 range max. Yeah, 100, 200. But I'm just really guessing based on hazy memory, so don't quote me on that.
Continues actually he said about 100 in the NISQ era. So excellent. And then someone else asked, when a circuit is sent to run on a quantum system, I'm assuming the real quantum system, are all the gates decomposed?
So all the gates have to be, yes, and 1 or 2 qubit gates that are supported by the hardware. So they will be decomposed. Yes.
Excellent. And then I think last question, unless anyone else has any burning ones at the end, but they said, what does the T in the formula for the X-Mon gates stand for? I mean, I suppose the theta is the angle of rotation. What T is representing?
Yes, it is. So here, this is exactly the angle of rotation. So in this form, when it's an exponential, you can think about this as the reason it's T, because you can think about this as a continuous evolution and it's time, like how long are you running the evolution, the rotation. You can think about it as the angle of the rotation as well. So in this case, it is the rotation around the z-axis for a single qubit. In this case, it's a rotation around this specific axis, which is determined by the theta angle that is on the xy plane. So you first get an axis, so that's the theta, and then you have the t, which then determines the rotation around that axis that you just got. I hope this answers the question.
Excellent. Well, I think that's all the questions that we have now. I just want to thank Balint again and Tanuj for such an excellent presentation. For those who are watching live right now, you guys can actually, I'll say something and then I'll finish up. If you want to say one last thing.
No, thank you so much for the opportunity for presenting here. Thank you, Tanuj, and thank you for the whole all the organizers. This is an amazing event, and then good luck for the hackathon for all the participants.
Yeah, and thank you everyone for attending. It was a great experience organizing a hands-on workshop in an online fashion. Like I mean, we also like this was our first attempt, and hopefully like we didn't do very bad. So yeah, thank you for attending.
Yes, true. It was first for both of us. So
I can say from my perspective, and I've been obviously watching the whole time. It's been amazing. Just I kind of wish that I was a participant. I think Sean said something the same, but watching this, I wish I was a participant and I could like do this kind of stuff. But I probably will watch the recording at some point later tonight or tomorrow and go through some of these, even though I think I already know the answer to them. But other than that, thank you guys so much for tuning in live. We will be obviously putting this recording on Twitch for you to see. I know some people were commenting that we were going a little fast. We were a little pressed for time, but feel free to go back at the Twitch and look at whatever you want and learn. But yeah, so this is actually for QC Hack, the last event for today. Tomorrow we'll have a whole new slate of events. I think we have a social event and maybe a panel tomorrow. Don't quote me on that, look at the schedule. But yeah, thank you guys so much for tuning in, and we will see you tomorrow.